Okay, well, we'll go ahead and jump into it. I know there's folks still logging in, but and if you guys have any questions during the presentation, let's try and hold those, and we'll get to them after Andy's presentation today. So I'm going to introduce myself. My name is Paul Stevens. I'm a divisional sales director for Maya. And I've got about 20 years of experience selling Siemens products. And for most of that time, I've been selling NX CAD/CAM with an emphasis on NX CAM into industries such as aerospace, the supply chain for aerospace, some automotive suppliers, and defense contractors. And my better half on the webinar today is Andy Schaefers. And Andy is a senior application engineer at Maya. And I've been working with Andy for most of my time selling Siemens products, so almost 20 years. And he is our technical guru for both CNC programming and the CAM space in general. He's got about 15 or 16 years of experience, specifically with NX CAM, helping me to sell the software as well as training and consulting services. So I wanted to take a few minutes to introduce Maya and the webinar series that we're kicking off today. So I'll just go to the agenda here. So Maya HTT is an international channel partner, as well as a software developer for Siemens, with offices in the US, Canada, and the UK. And Maya is the largest channel partner in North America for Siemens, with over 220 employees and a diverse skill set and product offering. Maya's strength extends from design and simulation, and so far we've got about 500 simulation projects completed. And that's really where Maya got its start some 30 plus years ago, is with simulation products, CAE specifically. But it extends now to manufacturing, where we've got about 50 plus years of combined CAM experience in multiple industries. We also do IoT and applied AI projects, lots of software development, primarily for Siemens, but other customers as well, and product lifecycle management, where we've done about 150 PLM projects with Teamcenter so far. So that's Maya. And then I'm going to go ahead and talk a little bit about NX CAM in general, and then hand it over to Andy, where he will be talking specifically about the easy transition to 5-axis using NX. And then we'll sum things up, and there'll be some time for Q&A after that. So Maya, you know, we've talked about this before, but we've done a lot in design and simulation. In fact, that's where we spent most of our time, you know, for the first several decades. But now very, very strong in manufacturing. We're going to focus a lot on that today, and consulting projects all the way through to Teamcenter. So I just wanted to talk briefly about the broad value of NX in manufacturing. Siemens has software products, NX being the primary one, that covers everything from additive manufacturing to CNC programming, which we'll talk about today, designing tools for part manufacturers, quality control. NX has a CMM product specifically for quality. Robotic automation, we've got software to actually program the robots used on the shop floor, and tooling and fixture design. We also have a lot of products that help with shop floor integration and revision control and QMS compliance on the shop floor. So most of those we can talk about if you're interested, but today we're going to focus primarily on NX for CAM. So the CAM webinar series today will be an easy transition to 5-axis machining, where we'll talk about robust programming techniques and best-in-class work holding setup using NX assembly. So Andy will cover that today in a series of demonstrations. On February 4th, we've got CAM simulation and validation. So NX has an integrated simulation and verification tool that allows for true G-code based simulation and collision detection. We'll talk about that on February 4th. And then finally on February 11th, shop floor integration, which to me is a very important piece of this, this whole product set, allowing you to deliver shop floor instructions to the floor, doing QMS compliance and efficient work instructions. So today, the easy transition to 5-axis machining. Some of the challenges that programming managers have talked to us about over the years, implementing new programming techniques, work holding strategies, and tooling. And of course, your programs are getting much more complex. New validation techniques are necessary. And programmers must learn relevant skills, and shop floor policies must be developed. So in this session today, you're going to see an end-to-end 5-axis machining workflow, including tooling, programming, and validation. We're going to see a demonstration of best practices for swarf machining, multi-axis adaptive roughing, and multi-axis surface machining. And we're going to learn how NX CAM captures machining process knowledge and creates efficient programming environment with consistent results on the shop floor. So with that, I'm going to hand it over to Andy, and he can jump into the demo for you guys.
Okay, Paul, do we want to start with our first poll question here?
Yes, let me go ahead and launch that.
Go right ahead.
So we've got an open poll. If you guys can take just a few seconds to answer that, it gives us a better idea of what you're challenged with right now. So Andy, I don't know if you can see the results there, but.
Yeah, looks like lots of folks have a 5-axis machine, but it's currently underutilized, which sounds pretty typical to me. Everyone wants to make those machines more efficient.
Okay, Andy, I don't know if you can grab the screen at this point.
I'm hoping I just did that. Can you see my PowerPoint now?
Yes.
Okay, great. Thanks, Paul. Well, when you implement something new, you're always looking for ways that you can leverage your existing knowledge. That's something we handle really well in NX CAM with our 5-axis solution. We facilitate this due to the efficient way that our software is structured. Specifically, I'm going to demonstrate the tilt tool axis command as an example. Your programmers can start with a 2.5, 3-axis toolpath and then convert it into a 5-axis toolpath. The result of that is a smooth, efficient operation where we minimize the machine rotation. Here's a core for a plastic injection mold. At first glance, this certainly looks like a part that can be machined using 3-axis. So that's where we'll start. However, in a few minutes here, we'll find that this might actually be a candidate for 5-axis operations. As you can see, I've already got my tools created. There are 12mm ball end mills, and the 05 is short, the 06 is quite long. Okay, I'm going to use the Z-level profile operation. And I have my steep containment set to 60 degrees, so it's only going to machine the steeper areas. Here in the non-cutting moves, I'll turn on the override with smooth connections, and let's generate. Well, the upper part certainly looks good. but we're having issues as we get lower down on the part. And of course, what's happening is with the short tool, the holder is bumping into the wall at certain areas. If we go to verify, we can see that more clearly. So it really isn't getting into these notches at all. Here's a quick fix for that. We can go and replace that short tool with a longer tool. So that's a pretty nice tool path. However, when we look at the tool, we see it's quite long. It's not going to be rigid, and we're going to have to slow our feed rate down if we want to have a good surface finish. So at this point, we don't seem to have good solutions for machining this part. This is where tilt tool axis and the 5-axis capabilities of NX can come in. I'm going to switch back to that shorter tool. But here in collision check, I'm turning off all checking. So it's going to machine it as if it would actually work. But when we look at the results, we'll see that, of course, that tool is colliding in many areas. I'll just verify it to show that to you. So we can see here it's running right into that wall. Okay, so now I leave that operation, and at this point I right-click and look for the tilt tool axis, which is a command external also to the operations in NX. That means that I can use tilt tool axis on any 2 or 3D operation. Here I want to change my clearances to 0.5 millimeter. And when I click OK, NX will run through the entire operation, looking for collisions at each point and tilting the tool axis away from the wall to make the toolpath work correctly. Okay, there's our result. Let's evaluate this now. We can see that in areas where there's no clearance problem, the tool axis has not changed. It's still straight up and down. But as we get into areas where there is a potential collision with that tool holder, you can see that it's slightly rotated it out away from the wall. And even down here, we've got the correct result with just a very slight rotation. Okay, that's a huge advantage then, to be able to take any 2 or 3-axis toolpath and turn it into a 5-axis toolpath. Okay, next up is a discussion of guided curve machining. Tool axis control is probably the single biggest hurdle to overcome when you're trying to implement 5-axis programming. In this next demo then, I'm going to continue that theme of an easy transition for your programmers. What's significant about our capability is that we break the programming process into 2 pieces. First, we're going to set up the helical toolpath around the part with a simple instruction for a normal tool axis. Then we'll see that we have a collision on the bottom side of the part, but we deal with that collision as a second step. Again, we're going to have the tilt tool axis involved, but it's going to be part of the operation this time. Let's look at the demo now. For this part, we'll be machining the aerodynamic surface here on the right end. We'll use a 2-step process where first we create an operation where the tool axis will be normal to the surface. This is a ball end mill, and you can see that's going to create some problems back here where we'll be colliding with the flange. The second part of our process is to use tilt tool axis to resolve those issues. We're going to use our multi-axis variable guiding curves command to do this with. This command will allow us to morph between two curves. We'll select these two curves and create a smooth toolpath between them. But the first step is to select the 4 surfaces that we're actually machining. Next, I'll select the morphing option, and then here's the 2 curves. Okay, the pattern I want is helical. You see I've got several choices here. Next, let's look at the axis. This should already be set up correctly for us, but we wanted our tool axis to be normal to drive. And for our first time through, when we see a collision, we just want to report it. So let's generate this toolpath now. And I should point out we're using these clearances here to determine whether there's a collision or not. Okay, there's our toolpath, and in red, we see the areas that, as we expected, are creating a collision with this flange. So those are the problems we've got to solve before we can continue. Here I'll use tilt retract. And I do need to make a change here in machine control because this axis of the machine is actually X, not Z. So I want to tilt away from X. We'll just regenerate again. Okay, there's our completed toolpath. Let's evaluate this then and look at how NX handled this situation. So we can see that in areas where there's no collision, our tool is normal to the surface as we expect it to be. But as we get to problem areas down here, it starts to tip that tool away. As we would expect it to. Okay, now I'm going to skip ahead in the video a little bit so I can show the 3D verification of the last part of this, just so you can see how the tool axis changes. Okay, we start to see the tool changing its axes. Just a little bit more as it encounters the wall on the bottom side. But it's always trying to return to that normal tool axis whenever it can. But it's not jerky, it's a very smooth motion that's going to run well on the machine. All right, that's tilt tool axis, then used in conjunction with the variable guiding curves command. Our next subject is multi-axis roughing. And when you look at the geometry over on the right side, you can see some of the challenges that we face with multi-axis roughing in terms of trying to achieve an efficient toolpath. Here our floor is curved and the walls are not parallel to each other. So it's a challenge if we want to use an adaptive style toolpath with a constant chip thickness. But that's really what we're looking for to get efficient programs and longer tool life. We've got a an operation in NX that handles multi-axis specifically. And when you see one of these run out on the shop floor, you'll really stop and think, okay, that's why we bought this machine. Let's watch the demo now. Here's the part that we'll be using to demonstrate multi-axis roughing in NX CAM. To see the benefits of multi-axis roughing, it might help to visualize the result we would get if we tried using a fixed axis adaptive roughing routine here. Because our floor is curved, we'd end up having to just assign a tool axis somewhere. And because the walls are sloped at different angles depending on which location you're at, we'd end up with stair-step areas of material on the sides and areas of the floor that didn't clean up. So I think you can kind of see the benefits then of having a 5-axis roughing routine where we can adjust that tool axis locally based on what's going on with the walls or the floor. I think you'll also be surprised at how few inputs are required to make multi-axis roughing work out. So the first thing I'll do is select this floor. And the next thing I need to do is limit the area that can be machined. So I'll use a containment loop so that it does not try to project that floor all over the part. Now let's go back to the main again, and we already have adaptive selected, so it's time to generate. Okay, there's our toolpath. And the first thing you probably notice is that that's a very coarse step over. It's 60% of the tool diameter, which is way too much for an adaptive milling technique. Probably should be more like 8 or 9%, but it generates faster when I do that, and it's a lot easier to see what's going on in the verification. So we'll leave it like that for the rest of the demo. Let's do a 3D verification now so that you can see how this runs. We'll start with a helical engage, and you'll actually see the tool axis change immediately. If you look at that closely, you can see it changing right now. It's going to finish out the bottom, and then we'll do the kind of the arcing routine to work our way up to the top. And as you see this clean up, and again, imagine what a 2D toolpath would look like roughing this out. I think you can really see the benefits that not only having a 5-axis machine, but having a powerful 5-axis program like NX CAM could mean for your business. Okay, that was our 5-axis roughing. We're switching gears now to circle segment tools. And Paul, we have a poll about this, but I think because circle segment tools are sort of known under different names, I'm going to do this section first, and then let's run the poll right afterwards. But these tools are not new, certainly. They've just become increasingly popular due to the synergy with 5-axis machining. We can simulate the finish of a much larger diameter tool with these circle segment tools. So why are they popular now? Well, the way to get the efficiency out of them is to be able to put the contact point somewhere on this larger radius. Well, with a 2.5-axis or 3-axis machine, very difficult to do that for most geometry. But with a 5-axis machine, we can orient and put that contact point where it's needed so we get the maximum material removal as we're going past. Now, in the shops, if we can see like a 5 or 6% production increase in something, we're usually happy to take that. But these tools, in some cases, you can reduce the number of finish passes by 3 or 4x. That's a significant opportunity that just doesn't come along very often. So what we're going to show here is our capabilities for using these tools that really just mirror the standard operation types your programmers are already going to know how to create. So again, let's get started on the demo here. Here's the impeller that we'll use to explore the solution for circle segment cutters in NX-CAM. I've already got an operation created here, but it's not for the circle segment cutter yet. We're going to start with a ball end mill and work our way up to that circle segment cutter. As I select, you can see the toolpath moving horizontally along this concave surface of the impeller. And you can see here that the toolpath is truncated. I think if we put the tool on one of those areas, we can see what the problem is. And here is the limiting factor in machining these vanes. The tool diameter can never grow very large because eventually it's going to hit the corner here of the adjacent vane. So this looks like a perfect situation for using a circle segment cutter where the large radius on the side of that cutter can then approximate the usage of a much larger diameter ball end mill. Let's go inside this operation so that you can see the key decisions I made and the features in this operation that allow it to work well. The first thing to look at is our drive method. I've chosen the surface of the vane to drive, so that's where NX is going to get its information to determine the direction of these machining curves. Now, another nice feature here in surface area drive is the ability to limit the surface. If you look at it carefully, you can see it actually goes, the surface goes under the part, which of course I don't want to machine in this top operation. And I can limit that with this end step here. In fact, I also showed how I could limit from the sides by 3 percentage points. So that's why you see the toolpath doesn't quite make it all the way to the end. Now, of course, it will still check to things like this tab here or these features here, but sometimes it's nice just to be able to use a surface percentage, and this interface makes it really easy to do that. Now, let's look at some other features here. I've chosen 10 step overs, and I'm using a zigzag, which you see reflected here. Next, let's go look at the tool axis. I'm using a swarf drive, and a swarf drive will get its orientation from the internal constriction of the surface. It doesn't work well in all situations, but when you have an organic shape like this, a swarf drive is often going to give you the smoothest results. Now, I've tipped the tool away from the surface locally by 10 degrees. So that's what the tilt angle is here. Then I've got some clearances, and those clearances would have impacted where the toolpath was truncated before hitting the surface here. In other words, it didn't go right until a collision. It went until the tool shank got to within 1 millimeters of that wall. Okay, then let's look back at the main again, and you can see that I've left 0.15 millimeters of stock. Again, this is a semi-finish operation. So let's go ahead and verify, and we can see all these settings as they act on our final result. Okay, I'll switch over to 3D dynamic. And I've just got some local stock here created. Let's slow this down a little bit more. Okay, there's our completed toolpath. You can definitely see the material that's left there when the tool picked up to get around that obstacle. And we can see that even with the 10 toolpaths, the scallops are actually quite heavy here. Okay, at this point then, we want to look at that circle segment cutter. We actually call it a tangent barrel here in NX, But the nice thing about this setup is we make it really easy to get the values out of your tool catalog and put them in directly to get the correct tool geometry that you want to use. Okay, now it's time to look at how we can reuse the knowledge we gained from creating this operation for the 6mm ball and apply it to the tangent barrel. Well, the first thing to do is just to copy this operation. Then I'll right-click on my circle segment cutter and paste inside. There are a couple things I need to change though before I generate. The first thing is, this is a finished pass, so I'm going to change my part stock to 0. And then in the axis and avoidance, I'm going to change that tilt angle to 9.5 degrees. Tip the tool just a little bit closer so that the contact point on that circle segment cutter moves up a little bit higher. Okay, let's generate and look at our result. Great, there's our toolpath. Let's just look at one of those contact points, and you can see, in fact, it is contacting up here somewhere on that circle, so we're probably getting a nice finish pass here. The next thing to do would be to verify that. I'll run the 3D verification, and we'll be able to see our circle segment finish tool working against the passes that were left by the 6mm ball. Here it's just computing what that looked like. Now you can see even with just 2 passes, the scallops are really much less pronounced than they were with the ball end mill. Remember, we used the same number of passes for both tools. It's really a dramatic difference in the amount of cleanup you're able to do with one of these circle segment cutters. Let's hit Analyze. So we can actually evaluate the finish on that surface. Okay, here's our gradient display. I'll change my legend just a little bit here. And let's take some individual measurements. So there's 0.008 millimeters, 0.15, negative 0.001, so that's at finish. So we're really very close at finishing this surface. Maybe just if we'd gone 12 or 13 passes instead of 10, we'd probably be done here. So just wrapping this up then, this is our solution for circle segment cutters and 5-axis machining. Okay, Paul, let's kick off that next poll, the one for the circle segment tools.
Okay, I'm going to go ahead and launch this here. And I'm just give it a minute here for everyone to answer the question. Okay, Andy, I don't know if you can see the answers there.
Yeah, this one is somewhat inconclusive, Paul. Looks like we're seeing justification and process issues being the main ones, and then cam system deficiencies being a minor problem. Well, Paul, I'm still an advocate, but I acknowledge there are some challenges for sure getting them to run correctly as part of your process. All right, let's continue. we're moving away from programming for a second and into issues regarding job setup, which is really important, particularly on short run jobs where volume is small, we're not sure we're going to get the job back, and we're looking for a way to make money on these small volume jobs. We need to be able to process them efficiency because we really can't optimize the process later. There is no later. There's no guarantee that these jobs are going to return to us. And we face a situation where the customer might change geometry, or there might be changes to the quality requirements, and we need to respond to those changes quickly. This is a big topic, and we're not going to try and address it all right now, but I am going to break out just one issue, and that is when we're doing tab machining, the actual creation of those tabs. And I'll show you a technique where inside NX we can automate the creation of those tabs and also make them easy to change if a requirement comes through for a modification. Here's the part that we'll be working with. We're just going to imagine the setup for this part being machined out of a billet with minimal fixturing. So we'll use tab machining. The tabs allow the part to be suspended inside the billet during the machining operations. At this point, I would usually be using CAD techniques to model the tabs one at a time and work my way around the periphery. This is a perfect application for the new algorithmic modeling inside NX. And in fact, I made my own custom application, which you see here on the screen. It's my tab creator. I'll walk through it one step at a time. First, I select the curve that represents the periphery of my part. Then I have the number of tabs and an offset, which is really like a clocking angle. Next is the orientation. It needs to know which way is up inside the billet, so that Z-axis will perform that function. Then there's some information about just the geometry of the tabs. At this point, I'll hit show result and we'll look at what it does. So it's created the tabs, but you can see that down inside the round there, they didn't really go back into the material far enough. So I do have an option for that. If I back these in another 2 millimeters, you can see it takes care of that. But probably what I'd really like to do is move the tabs up above the round. So here I have a Z direction offset. So let's look at that. Okay, that's much better. And at this point then, I'll click OK to accept that. Well, the nice thing about the algorithmic modeling, or one of the nice things, is that when you're done, it doesn't just create a bunch of geometry. Everything stays together as an associative feature. So you can get back to it in the future if you need to make modifications. And it will retain its associations to the CAM side once all the operations are created. So let's imagine that we've discovered that this is a high tolerance surface and we really don't want to tab here. It's going to be difficult to clean that up in that position. So we want to change that clocking angle. Well, all I have to do is double click on the algorithmic feature again. And we'll change that pattern offset value from 50 down to 5. Let's preview again, and it looks like we've got those two centered around that curved surface now. So we'll accept, and that's all that's required to make an edit to those tabs once they've been created. Algorithmic modeling is very useful here and has a lot of other applications in manufacturing. Okay, Paul, let's kick off our last poll as we're right between the two areas where we're talking about fixturing.
Okay. So I'm launching our last poll here. It'll take a few seconds to answer those questions. Okay, it looks like most everyone has answered that. Andy, I don't know if you can see the results there.
Yeah, I sure can. And I guess that kind of surprises me a little bit, but maybe it shouldn't. 2/3 of our respondents are making their businesses work with minimal fixturing in 5-axis. So we're seeing a lot of lower volume jobs created from billet stock, I'm guessing, and it's important to make those profitable. So certainly drives home our points about the need to be efficient with your setup process. Let's continue here though to our next topic. And that is CAM setup and fixtures. And our goal here is to create a setup that matches what's on the shop floor. This is not only for shop floor documentation, but if we're going to have an accurate simulation, we need fidelity between the fixtures in the CAD system and what they're building out there on the floor. So we can deal with a mix of purchased components that are coming out of a library and then custom machine components that are specific to a job. Now I'm going to demo this here pretty quickly. The situation that we're looking at is where the programmers have copies of a standard Vise geometry that's in a library. And typically what we see is these Vises get copied all over the place. There's a separate copy of the Vise in every different project directory. And the reason this happens is that programmers are afraid if they go back and change that assembly in the library, well, it's going to mess up all the other projects. But what we're showing you here is a technique in NX where we can have all these components in a library, including these Vises. When you bring them into your individual project and it's time to set the position of those Vise jaws, we have a way to make that Vise position unique within the project. Doesn't affect what's in the library. Huge advantage here because now you can really organize things with a library, but still meet the functional requirements of getting those Vises or other fixture elements to appear correctly, again with the fidelity to what's out on the shop floor. Let's watch the demo now. Here's the manifold part. We want to create a setup for, we'll hold this part in a vise. And so my first step probably is to create the billet stock, which we'll be clamping on. I'm going to use the bounding body command. All I need to do is select my geometry and it creates a rectangular shape bounding that. And I want to offset by at least 1 millimeter, but also round my numbers off to 1 millimeter. So you see that reflected here. Now, because we're clamping at the bottom, we probably want to add some additional stock. So I'm going to use the move face command. It's one of our synchronous tools. All I need to do is select the face on the bottom, and I want to offset a distance of 4 millimeters. You'll see it just drops that face down for me. Okay, we're ready now to place the vise. Okay, the long vise that I'm going to use comes out of a library. It's one I use frequently in projects. And I'm going to display it here in a preview window. This often makes it easier to choose the faces that relate the vise to the component. So here I can choose the bottom of my billet. The next thing I want to do is quickly center the billet inside the vise. Well, there's a command that does that also. It's just called center. I'll start here with the 2 sides of the vise and the 2 sides of the billet. At this point, let's turn preview on and we can see that we're very close to having this completed. The next thing I'll do is look at the front and back of my vise jaws. So I'll select here. And it looks like we might be complete, except there's a problem. The opening of the vise jaws does not match my billet. Now I could go into this vise assembly itself and change that, but that might change how the geometry looks in the other jobs that use this vise. What I want to do is change this uniquely only for this situation. And NX allows me to do that. I can just override the position. But there's something else that we need to think about. this is a self-centering vise, so I don't want to just move this jaw over. Well, I think you'll see that this is going to work correctly because the vise has a relationship in it already to make sure it works out that way. So I'll just select this face here, this face, and we can see that in fact both jaws move just slightly to bring the jaws against the billet while at the same time keeping those jaws centered. So that completes the placement of the vise. The last thing to do is place an adapter plate. That's also off in our library here. I'll use that preview one more time. You'll see just how quickly I can accurately place this adapter plate on the bottom side of the vise. So now I've mated it. Let's find a center axis. The 2 pins. Now let's have a look at it here in the window. And it looks like I just need to rotate it, and I can use a parallel relationship there. Reverse, and it's placed. That's all that needs to happen to get that adapter plate on. There's probably some other plates that need to go on to create the tower to get this part off the table, but that's all the assembly we're going to do here in this demo. Next, we'll take on our final topic of the webinar. We want to talk about really putting the pieces together here, simulating our operations, our programs, and checking our posted code, making sure that that code reflects the requirements of our machine and our process. You do want to have confidence that the programs are correct, that they're machining the part completely, and that you have no collisions. That management of risk and uncertainty is a critical part of our process. And here in this next demo, I'm going to start showing you how we achieve that with NXCAM. We're going into a lot more detail in this one in the next webinar, which is next Thursday. Let's put all of our concepts together. You can see I've finished the fixture assembly by adding some additional components. And then of course at the top we have our part and our blank. I've also attached a machine tool that we will use for simulation. And this is a Haas UMC 750. Looking off to the left side, here's my program with the operations used to machine the part. We'll be focusing on this area where I've got 2 operations for finishing this pocket. The first one is a 5-axis operation, and I'll put the tool in a couple of locations so you can see this. Indeed, the machine is rotating to keep that tool parallel to the face here, so we machine that complete. The next operation down is a fixed tool axis. So here's just a ball end mill being used to finish that fillet. And what we're doing is sort of a zigzag type operation where we do a pass on the upper wall and then a pass on the floor and keep moving back and forth until we finish. Now, when we get to the posted code, here's our expectation that the 5-axis operation should come out as TCP, tool center point control. And the operation below it, that's a fixed tool axis, we expect that to come out as a tilted working plane operation. And what we'll see is that in NX, we don't have to do anything special to the operations to make that happen. The post will automatically see that situation and give us the output that we're looking for. So at this time, let's start the simulation. Okay, here's our simulation control panel, and we are seeing the execution view with basically 3 things. Some information about the current state of the program, then the G-code itself, and this is a very important idea, but in simulation in NX, we can call up the post in the background, write the code into a buffer, and then that code is used to generate the motion that you're going to see on the screen. That's very important, and it's really the only way to make sure that the motion you see in simulation is going to match the motion that you see out on the physical machine tool. The third thing we have here is our machine status with our different settings here for axes, so I can actually move the machine by grabbing one of these sliders, even change the rotation, and that can be nice just to get a feel for, you know, is your fixture too big, then you have enough clearance for everything. Okay, so let's begin, and I do want to check the code though here at the beginning. Remember, we were expecting to see tool center point control, and the G234, in fact, that's what Haas uses for TCP, so that's correct. So, one more thing I want to point out is we are seeing the IPW or in-process workpiece as it would be at this stage in the programming. So in other words, NX has looked backwards and said, well, what material would already be removed? And so it's giving me that current state of the model. This is very helpful when you're trying to validate a program because you don't have to go back and validate everything from the beginning again. In fact, just to demonstrate that, I'll turn off the display of the part itself. And so here we're seeing just that IPW or in-process workpiece. Okay, let's play. And the first thing we'll see is a simulation of the tool change. Probably went through that a little bit too quick. And let's slow that down. We'll get the tool change on the next one here. So it ran a pass on the outside. I'll turn on the display. Here's the toolpath that we're working towards with our G code. And here I'll create a tool trace. So the trace is being generated from the actual location of the tool historically. Okay, so we're just working our way around that wall with that finish pass. Now I have got things slowed down, so I'll show you the tool change here as we move to the ball end mill. So in our simulation, we can accurately reflect the way that tool change would appear. And here we are with our last operation. And in this case, we are just finishing out that fillet at the bottom. This is a constant tool axis. So I should be able to back up here and see that it's a tilted working plane. And in fact, it is. Here's G254. That is how tilted working planes are called out for the Haas machine. All right, let's continue. I'm not going to run this complete, but I want to place a couple of passes on the floor and the wall, and then we'll run another quick analysis. There's lots of options here with simulation that we're not going to have time to get to in this webinar, but our validation webinar is next week, where we're going to go through this in much more detail. Okay, I'm going to stop it right there. Let's go to the analysis, and we can kind of see pretty clearly that although we've taken some passes on the wall and the floor, there appears to be quite a bit of material in between that is still remaining on the part. And let's look at how analysis can help us determine that. Okay, I can use my gradient display, and that's indicating for sure that there's some issues there. But if I just click on the screen, I can get a measurement more exact. So there, I should point out I'm in millimeters, so that's actually a pretty small number. Yeah, so I'm near finished there, but let's click in the middle. And here we've still got, 100 thousandths 0.1 millimeters of stock remaining. So that indicates clearly that there's still some stock there. So our simulation does a great job of picking out collisions and other issues, but it's also really excels at communicating to you the areas where you have extra stock and more machining is required. Okay, that's our last demo for the webinar. Let's wrap things up now. All right, here's our wrap-up slide. Again, we just want to review our objectives today and reasons for considering NX-CAM as a solution. NX-CAM has been around for many years. It's a mature solution and has all the requirements to meet the technical challenges that you face in your shops. But beyond that, we understand that there's a lot of business challenges with creating a successful implementation of CAM in your shop. You've got to deal with programmers, process issues, customer issues, on. And the Maya team is ready to support you with any of that to help you get to that successful implementation with your new 5-axis machines. At this point, we're going to open it up for any questions that you might have.
So Andy, I don't know if you can see any questions or not.
I'm probably looking in the wrong place here.
So I might ask you a question, Andy, just verbally to kind of kick things off, and a few of these questions just come up from time to time as we do these presentations. But I wonder if you can answer, can NX set feeds and speeds automatically? I know that has come up.
Yeah, it can. There's really two approaches to that. One is that you can have a library where you've got your tool materials and your part materials and utilize that information to compute feeds and speeds on the fly. And the other, which is probably more common for our customers, particularly the ones doing low volume work, they want to assign those feeds and speeds to a specific tool. So there's a separate library for doing that. Now you get beyond that, Paul, and of course, we can set up templates. So if you had a specific facing operation, not only would you be setting feeds and speeds, the tool would already be assigned along with your step overs and your step downs. So all of that process knowledge can be captured in a single template if that's what the customer is looking for.
Thanks, Andy. I think maybe one of the things we didn't suggest is that everyone's on mute. So if you have a question, you can type it into the question section there of the GoToMeeting.
Right. Sorry, I was not clear about that.
Yeah, and there is a question about post-processors. Maybe you can tell us a little bit about the post-processors that are included with NX and how to get post-processors that are not included.
Okay. We do have some generic post and simulation kits that are shipped with NX, but we also have what we call our post hub. It's an online delivery where you go and search for your particular machine or your particular control to look for a post or sim kit available for your machine tool. And of course, we find that usually even if a post is a match to the machine that you have, you've got processes specific to your shop, the header information and things like that, that are going to need to be modified. And we've got a team at Maya, our services team, that is set up to take those requests and customize a post so it fits your process.
Thanks, Andy. I'll give you a specific question about a post. Does the Haas UMC 750 post come with the software?
Yeah, that's a great question because that's a really popular machine right now. And I know on the post hub, there is a UMC 750 that's available, but at Maya, the one that you saw in the demo today, that's actually one that I developed. So that one is available also. So I guess we have multiple solutions to that problem.
We do have another question that came up. Does Maya create posts using Post Builder or Post Configurator?
Well, we can use either technique, but Post Configurator is the go forward technology now, and personally, I think it's superior. So we would do either one for a customer, but our strong recommendation is Post Configurator.
Thanks, Andy. Any other questions? Oh, okay. Here's a question, Andy. In the CSE simulation was line with number 3026. Where is that stored?
Oh, okay. That's that's a variable from the Haas control, and so it's actually just a user variable that was handling the height offset. That was just a specific request that someone made for that post based on the way they want to run their height offsets on their machine. But the simulation works just like the control does. So if you have variables that you're working with out on the shop floor, we're simulating them in CSE. So that's where that's coming from.
Thanks, Andy. So far, I think that's all of the questions we have. So I think we'll go ahead and just wrap it up. This video has been recorded, so we'll be able to make this available in a different medium for all of you. And we'll be reaching out to you individually to kind of talk about the webinar and any challenges that you're having specifically in your business and how Maya can help. So look forward to that. And thank you, Andy, for a great presentation. I appreciate it.
Yeah, we know you're all busy. Thank you so much for your time today.
Thank you.